Hello friends, welcome to the course Essentials of Data Science with R software. And now you can see that we have learned the concepts of probability theory in different ways: simple probability, conditional probability, and we have used different types of theorems in the form of some results, additive theorem, multiplicative theorem, and so on. And you have seen that these theorems, results, concept, they are going to be applied in different types of conditions, situations, and you can draw various types of conclusions from there. That depends on your capability, how much you can dig out the information through these tools. Now, continuing on the same lines, today I am going to talk about a very important result in the probability theory. This is Bayes theorem. Believe me, this Bayes theorem is very important, and this is the foundation of the Bayesian inference. And you know that whenever we are trying to compute some probability, there are two possibilities: that the event is going to happen for the first time, or the event has already occurred in the past. For example, if I ask you that how much time do you take from going from your home to your college? If you are going for the first time, then you might not be knowing, but now since you are going to the same college for a long time, so you will say, okay, I will reach in say 20 minutes or so. How do you come to this idea? Or if in fact you can also say, if there is no traffic, then 15 minutes, if there is heavy traffic, then 30 minutes, and if there is a reasonable traffic, possibly 20 minutes, and so on. Now, if you try to see, if I ask you a simple question today, that how much time are you going to take, then will you compute the probability only on one observation, or you will try to use all this information somewhere inside your mind, somewhere in the background? You will try to capture that information, and somehow you will try to compute the probability, and you will tell me that what is the probability. For example, if I ask you that how much time I am going to take going from my hotel to the airport or railway station in a new city, means I am going there for the first time, but you are staying there for a very long time. So you will ask me at what time you would like to go. I will say, okay, this is at 5 o'clock in the evening. So that is going to be office time, people will be coming back, so it is going to be crowded. So you will, so whatever is the time, you will give me some more time in the sense the time taken at 4 o'clock in the morning when there is no traffic usually. What is that? You automatically computed that time taking into account the prior information. That prior information was there with you, and that information was collected either from you or your friends, or somehow you came to know that at 5 o'clock there is going to be a traffic and it may take longer time. And then you are trying to tell me that how much time I am going to take. So under these types of events, if you try to compute various types of probabilities, they can also utilize this type of prior information. And once you are trying to use the prior information, things are expected to improve, because you are trying to incorporate more information into the system. If you try to incorporate more information, well, the information has to be correct. Then you expect that your statistical inferences are going to be improved. So with this point of view, let me try to explain you here the concept of Bayes theorem, and then I will try to take a couple of examples to make you understand better. I will try my best, and you also try your best. So with this objective, let us begin our lecture. Okay, so now you already have learnt one thing. What was the law of total probability? And this rule says that if A1, A2, AM are the events such that A1 union A2 union AM is equal to capital omega, and AI and AJ, they are pairwise disjoint, that is AI intersection AJ is equal to phi for all I not equal to J1 to M. and probability of A I is positive for all I, that is obvious. Then the probability of an event can be calculated as probability of B, which is equal to summation I goes from 1 to m probability of B given A I into probability of A I, right. So, now if you try to see, I would try to use this theorem in getting the Bayes theorem. The Bayes theorem gives a connection between the two conditional probabilities, probabilities of A given B and probability of B given A, right. And in order to understand what this Bayes theorem tries to give you, what type of probabilities it gives us, let me try to take a very interesting example and try to show you that how it is used and what type of information it is going to give you and how it is different from the simple probability. Right. So, suppose there is a blood test and that blood test claims that it can check the absence or presence of a rare disease, right. And there will be some probabilities, this I will tell you, and there are two possible events related with this claim. The first event can be that the outcome of test is positive, and the event D we are trying to define as person has disease, right. Now, I try to do here one thing, that suppose I have some information that the probability that the person has disease and test is positive, that means probability of A condition on D, that is 0.999, right. And we have one more information, that probability that person don't has disease and test is negative, that is probability of A complement condition on D complement, and this is also 0.999. Now, as a common man, if you try to see, you are trying to say that in case if the person has disease and test is also saying that the person has the disease, that is the test is positive, this probability is 0.999, that is almost 99.9%. And on the other hand, in case if the person doesn't has any disease, then the test is saying negative, this probability is once again 99.9%. So, obviously, you will assume or you will feel that the test is excellent, test is very good. Now, what we try to do? We select a person and we make a test, right. And now, this person who is selected for the test, this person may or may not have the disease. So, we assume that the probability that the person has a disease is probability of D. So, usually this probability of D is going to be small, right. Why should I expect that every person has a disease? And suppose this probability is very small, 0.0001, right. Now, we want to know based on the outcome that whether the test is good or bad. So, now you know, the condition is this, you already know that probability of D, that is the probability of disease, is very small. Now, you try to compute this probability of D condition on A, that A has already occurred or A is true. So, now this probability can be written as a probability of D into probability of A given D divided by probability of D into probability of A given D plus probability of D complement into probability of A given D complement. So, now we have all these values and we try to substitute it here, right. We have this probability of D to be 0.0001 and the probability of this test is 0.999. So, we try to substitute it here and then probability of D complement will be simply 1 minus 0.0001 and probability of A given D complement will be 1 minus 0.999. And if you try to compute it, this probability comes out to be 0.091. What do you think now? You are saying that test is nearly 9.1% that the test is good or bad. Now, if you are saying that the test is nearly 9% reliable only, what do you think? The test is good or bad? And if you try to see what you have said earlier, in these two probabilities, here and here, you said the test is 99.9% good. But when you are trying to compute the probability that whether the test is good or bad, given that the probability of D is very small, this probability is coming out to be very less, nearly 9.1%. So, that means test is not dependable. So, what you have seen here, that if you are trying to use some prior information, some prior probability, then this is going to change the outcome. This is going to change the result, right. And these types of probabilities which are known to you a priori, they are called as prior probabilities. And up to now, we were looking only on the prior probabilities, and the probabilities which we have now computed, they are posterior probabilities. They are called as posterior probabilities. So, now the moral of the story is, do not rely only on prior probabilities, but also look for the posterior probabilities, and this Bayes' theorem will help us in the computation of such prior probabilities, right. So, this Bayes' theorem gives us a connection between the conditional probabilities of A given B and B given A. And for two events A and B with probability of A greater than 0 and probability of B greater than 0, we know that probability of A given B is probability of AB divided by probability of B, and now I can just multiply and divide this probability of A in this expression, and you can see here what is this thing, probability of AB upon probability of A. This is simply over here the conditional probability of B given A, right. So, now you can see here that probability of A given B is equal to probability of B given A into probability of A divided by probability of B. Well, you also had found such a result earlier by computing the probability of AB, right. So, now in case if I try to extend it, then suppose we have here M events A1 A2 AM like this, such that A1 union A2 union AM, that is equal to sample space capital omega, and AI and AJ are pairwise disjoint, that is I for I not equal to J goes from 1 to M, AI intersection AJ is phi, right, and probability of AI is positive for all I. And suppose B is another event than A, then in case if I want to find out the conditional probability of AJ given B, then using this result which was only for two events, this can be extended to M events, and we can write down here this as probability of B given AJ into probability of AJ divided by summation of I goes from 1 to N, probability of B given AI into probability of AI. And this formula is known as the Bayes formula, or this is called the Bayes theorem, and this is actually based on the name of an English philosopher Thomas Bayes, who had given this formula. And here these probabilities what we have written here, this probability of AI, they are called as prior probability, probability of AI given B, they are called as posterior probabilities, and probability of B given AI, they are called as model probabilities. So, now we take some examples to understand the application of this law of total probability and Bayes theorem. So, the first example is like this. Suppose someone rents books from two different libraries, and sometimes it happens that the book is defective due to missing pages. So, here we consider the two events A1 and A2. So, A1 is indicating that the book is issued from the library 1, and A2 is indicating the event that the book is issued from the library 2. And suppose B is the event that the book is available and is not defective, right. So, now we assume that we know that probability of A1 is 0.6, probability of A2 is 0.4, and probability of B given A1 is 0.95, and probability of B given A2 is 0.75. And based on this information, suppose we are interested in the probability that the rented book from the library is not defective. We want to know this probability. So, now if you try to apply here the law of total probability, then we can use the formula here, that probability of B is going to be probability of B given A1 into probability of A1 plus probability of B given A2 into probability of A2, and if you simply try to substitute all these values over here, you get here the value to be 0.87. So you can see here that this law of total probability is helping you in computing this type of probabilities. And we may also be interested in the probability that the book was issued from library 1 and is not defective. So this type of probability can be computed by computing the probability of B intersection A1, which can be expressed in terms of conditional probability, such as probability of B given A1 into probability of A1, which is 0.95 into 0.6, which is 0.57. And now suppose we have a non-defective book issued, and suppose we want to know what is the probability that it is issued from the library 1. Right. So this can be obtained by computing the probability of A1 given B. So that is equal to probability of A1 given B divided by probability of B, and this can be computed here as 0.65 after substituting these values. So you can see here from this example, I am trying to give you different types of events that can be computed. And similarly, if you assume that we have a defective book, somebody has got a defective book, that is B complement event occurs. Now we want to know that suppose the probability that a book is defective given that it is from library 1 is given by probability of B complement given A1 is 0.05, and suppose the probability that a book is defective given that it is from library 2, this is probability of conditional probability of B complement given A2. So this is 0.25 for library 2. Right. Now we can now calculate the conditional probability that the book is issued from library 1 given that it is defective as follows. Right. So you can see here that we want to find out the probability of A1 given B complement. So this can be written using the Bayes theorem, that probability of B complement given A1 into probability of A1 divided by probability of B complement given A1 into probability of A1 plus probability of B complement given A2 into probability of A2. And if you simply try to substitute all these respective probabilities over here, then you get the value here 0.2308. Now, and similarly, if you want to know the result about the probability of B complement that we have used couple of places, then you can use this result directly. Probability of B complement is equal to 1 minus probability of B, and you can obtain the value here 0.13, no issues. So now after giving this a couple of examples through this example 1, let me try to consider one more example. Suppose at a certain stage of a criminal investigation, the inspector in charge is 60% convinced of the guilt of a certain suspect, that somebody has made a crime and the corresponding police officer is 60% convinced, right, that possibly that person has done this. So suppose now there is a new piece of evidence and that shows that the criminal has a certain characteristic, such as the criminal is left-handed, means he or she works from the left-handed, beardless, that the number of hairs on the head, brown hair, etc. That type of information somehow becomes available from somewhere, and if 20% of the population is possessing this type of characteristic, we want to know that how certain of the guilt of the suspect should the inspector now be if it turns out to be that the suspect is among this group. So how to compute this type of probability, that you will see, that is a very interesting example, and you will try to see that how this Bayes theorem helps. So we try to consider here two events, G and C. So G is the event that the suspect is guilty. So G is coming from the G of this word guilty, and C is the event that he possesses the characteristic of the criminal. So the C is indicating the criminal. So that is easy for you to remember. So now we have that probability of G given C can be computed by probability of G intersection C divided by probability of C, and so probability of G intersection C can be written as probability of G into probability of C given G, which is equal to 0.6 into 1, which is equal to 0.6. So now we have supposed that the probability of the suspect having the characteristic, if he is in fact innocent, is equal to 0.2. So now to compute the probability that the suspect has the characteristic, we condition on whether or not he is guilty, and we try to find out probability of C, which is the probability of being criminal. That can be obtained as probability of C condition on G into probability of G plus probability of C condition on G complement into probability of G complement, and if you try to substitute all the respective probabilities, you get here the value 0.68. Now, using these two values, probability of C and here the probability of GC, what you have obtained here, you can obtain the probability of G given C, and this comes out to be here, if you try to substitute all the values, 0.882. So, now we can conclude that the inspector should now be 88.2% or nearly 88% be confident of the guilt of the suspect. You can see that how Bayes theorem has helped police personnel to investigate a crime. Right. Now, let me try to take here one more example to make this Bayes theorem and its application to be more interesting. Suppose a plane is missing and it is pre-assumed that it was equally likely to have gone down in any of the three possible regions. Yeah, may God forbid that this may happen, but if it happened, then people are trying to have a search operation. So this is based on those things. So in these cases, we have the probabilities actually which are the constants, which are pi, they are called as overlook probabilities, because they represent the probability of overlooking the plane, and these probabilities are generally attributable to the geographical and environmental condition of the regions, right. So this 1 minus pi is going to indicate the probability the plane will be found upon a search of the ith region, and when the plane is in fact in that region, that means suppose we suspect that the plane has crashed in this region, and we want to know it. So in such a case, we want to know the conditional probability that the plane is in the ith region, given that a search of region 1 is unsuccessful. Right, you can see, I mean, these types of things are very common whenever there is an accident. People try to look for such a site and they try to investigate from starting from some place. So they want to compute this type of probability, they will be very helpful to them. So we try to use the Bayes theorem to compute such probabilities, and let us try to see what happens. So let this Ri, means R1, R2, R3, these are the three possible regions. So this Ri be the event that the plane is in the region I. And suppose this E is the event that a search of region 1 is unsuccessful, that is given to us. So now using the Bayes formula, we can obtain probability of R1 given E, probability that the plane is in region 1 given that the search of the plane in region 1 is not successful. So now this can be obtained as probability of E intersection R1 divided by probability of E. And now using the Bayes theorem, you can rewrite this probability here as like this, a simple extension. And now I try to write down here these values, that this the probability P1 into 1.3, and I try to substitute here all the conditional probabilities and the another probabilities of R1, R2, R3 here, and we try to compute this thing. This comes out to be P1 upon P1 plus 2, right. And similarly, we can also find here probability of R2 given E and probability of R3 given E also. So that will also give us the probability of the event that the plane is in region 2, given that the search of region 1 is unsuccessful, and similarly the plane is in region 3, given that the search in the region 1 is not successful. So you can compute it exactly on the same line. The probability of Rj given E is equal to probability of intersection of E and Rj divided by probability of E, and if you try to simply substitute all the values as you have done earlier and try to substitute all the values, this will give you here the values 1 upon P1 plus 2. So for example, if I say if the value of probability 1, that is the P1 is 0.4, then the conditional probability that the plane is in region 1, given that the search of the region did not uncover it, is simply 1 by 6. You simply have to just put this value out there, right. So you can see here that this type of application will indicate that how you can apply them in different type of situations which you are trying to handle in the data sciences, right. Now I come to the last example on Bayes theorem, and that is also an interesting example that many students try to do it. Well, they have a very different type of belief, and now I am going to show them that their belief is right or wrong. You know that whenever we are trying to attempt a multiple choice question in an exam, then sometimes we try to make a guess, and based on the guess we try to choose the correct answer. So, this example is related to that one. Right. So, in answering a question on a multiple choice test, a student either knows the answer or the student makes a guess. So, let small p is the probability that the student knows the answer, and 1 minus p is the probability that the student makes a guess. That means that the student does not know it, as simple as that. So, assume that a student who makes a guess at the answer will be correct with probability 1 upon m, where m is the number of multiple choice alternative. You know that as a student that sometime if there are 4 alternatives, and then you say many times that if there are 100 questions and if you tick at random to them, you will get 25 correct answer approximately. So, these types of statements are very popular among the students, right. So, now you will see what really happens. Right. So, this is the same statement that what if a question has 4 alternatives, then we are assuming that a student who makes a guess at the answer will be correct with probability 1 upon 4. Right. So, now we want to know the conditional probability that a student knew the answer to a question given that he or she answered it correctly. Right. So, now that is a very interesting problem for you, I am sure. So, now suppose there are 2 events C and K. So, C is the event that the student answered the question correctly, and K is the event that he or she actually knows the answer. Now, we try to obtain here the conditional probability of K given C. That means the conditional probability that he or she actually knows the answer given that the student answers the question correctly. So, now I can write it down here, probability of K intersection C divided by probability of C, and using the Bayes theorem I can write down here probability of C given K into probability of K divided by probability of C given K into probability of K plus probability of C given K complement into probability of K complement. And if I try to substitute all the values over here which we have assumed, we get here this answer. So, now if you try to see here that if you try to assume that there are 4 alternatives, and if you try to substitute here m equal to 4 and suppose p is equal to 0.5, then the probability that a student knew the answer to a question he or she correctly answered is simply 4 upon 5. Right. So, now you can see that possibly this is a different result than what you expected. So, that is the main use of this Bayes theorem, right. And now, let me give you here one more example. And suppose a laboratory blood test is 95% effective in detecting a certain disease when the disease in fact is present. However, the test yields a false positive results for 1% of the healthy person tested. What is the meaning of false positive? That means, if a healthy person is tested, then with probability 0.01 the test result will imply that he or she has the disease, right. So, if you assume that 0.5% of the population actually has the disease, then we want to know what is the probability that a person has the disease given that the test result is positive. So, this is the same example by which we started, and now we are trying to come to this thing, right. So, now in this last slide or the last example, we assume that here there are 2 events D and E. So, D is indicating the event that the tested person has a disease, D means disease here, this is how I have defined it, and E is the event that the test result is positive. So, now the probability that we want to compute is given by probability of D given E, and using the Bayes theorem we obtain it, probability of D given E as probability of D intersection E divided by probability of E, and using the Bayes theorem we can write it like this, and we try to substitute here all the values what are given to us, and we try to compute the probability. This comes out to be 0.323 approximately. So, it is indicating that only 32% of those persons who test result are positive actually have the disease, right. So, we expected that this figure should be much higher, because blood test seems to be a good blood test. Good in the sense that if a person has a problem, it will say yes there is a problem, or if not, the blood test will say no, there is no problem, but there are 32% chances, which is not a small value. Right. So, now I come to an end to this lecture with this Bayes theorem. Well, I have tried to give you the statement of the Bayes theorem, And I have taken a couple of examples to make you convinced that how this Bayes theorem is very useful in real application. Now, if you try to see, either this is conditional probability or Bayes probability, anything, the entire probability function is going to be a function of these individual probabilities, right. So, that is why it was very important for me to give you the information on different types of probabilities. And now you can see that as you are going into deeper and deeper, you are getting a better results. Now, if I ask you that for a given incident, if you have to choose simply the simple probability or the Bayes probability or the conditional probability, you know that how the results are going to be changed and how they are going to impact the outcome. So, now I will say, try to look into your assignments, books, and try to take some example. Try to understand them, and more important part for you to understand is how these individual values are coming. How are you going to translate that what is A and what is A complement, what is A given B and what is B given A. That is the job of a data scientist. The data will not raise its hand and say, okay, in this case you please find out the conditional probability of A given B or conditional probability of A given B complement and so on. Now, one thing more, that this conditional probability is just like simple probability, which is having some nice properties, and all those rules about these conditional probabilities are there. But definitely if I try to take all the topics over here, means we will miss some other important topics. So, I will request you, why don't you take up a book and try to compensate that part which I am unable to do here in this course. My objective here is something else, so I am doing it from that point of view, but definitely by saying this I cannot say that the topic was 100% complete. So, that depends on you how much you now want to learn the statistics so that you can use it in a much better way in a data science. So, you try to practice it, and I will see you in the next lecture. Till then, goodbye.